Thank you. So as you said, my name's Seth. This is Cliff. We work at MediaMath. This is kind of our story, the last 10 months building a real-time reporting system using Apache Flink. I'm not going to read all of this, but basically MediaMath is an ad tech company based in New York. We're a demand-side platform, which means we work with advertisers to get their content onto various digital platforms through a process called real-time bidding. Specifically, we work on the reporting team. And we're interested in generating the data that powers our user-facing reports. We have multiple different data streams that, or raw log streams that power this. We started by just kind of focusing on one for this project. It's our impression logs. It's what ads have we shown at what prices. We'll see between 600 million and 1 billion records a day, depending on the time of year. But of course, would hope to expand to other data sets as quickly as possible. So this data is collected from multiple data centers around the world where we have these very low latency bidders. But we do all of our work inside of AWS. And so this project started with the idea that, we're gathering data, We're gathering data constantly throughout the day, but we're only actually generating our reports several discrete times in these batch processes. Wouldn't it be great if we could constantly update, right? I want to see exactly where my money's going, and so I can make decisions as fast as possible. And we started by saying, all right, let's take the logic from our batch processes, rewrite it using Flink's API, see what we get. And it was okay, but like the squirrel in this airplane, it very quickly got away from us. Right? We were getting the correct results, but our latency wasn't so great. We weren't incredibly fault tolerant. But it seemed like there was something here and something worth doing right. So we came up with a couple requirements of what it was going to mean for us to be production ready with this system. First is we did not want a lambda architecture. So I know this has been touched on a couple times today, but a lambda architecture is where you have some really fast stream process that gets you data as quickly as possible, but it's not going to make any hard guarantees on data accuracy. Instead, you'll have this batch process in the background that says, all right, I'll go and clean things up later in the day. The problem is our data really represents financial transactions. We are telling people how much of their money we have spent. And so you can explain to clients till you're blue in the face what a lambda architecture is, but the first time that they see that we spent $100 and then the batch process runs and it jumps up to 1,000 because we just happened to drop a lot of records that day, you're going to get some angry phone calls. So we need something that was going to give us the correct answer the first time every time. In fact, we wanted something that was going to be within 0.01% of what we were currently getting out of our batch processes. We have to fit into our existing stack. So we've got a lot of infrastructure in place. There's methods for getting data from our data centers into Amazon with very high consistency guarantees. We have databases with APIs built around them. We can't just throw that all away. This thing needs to be affordable. If we're going to go from having some process that runs several times a day to an always-on cluster, we have to make sure that we can actually afford this thing and we're not going to blow our budget for the year in the first 3 months. And finally, Cliff and I are the only two people that really know how this thing works. So if something breaks at 3 a.m., we're the ones getting phone calls. I like my sleep, and so we need to make sure that this thing is fault tolerant, resilient, and will self-heal in the face of a real disaster. So we start just kind of looking at what our current infrastructure looks like. We have these bidders out in the world, they're doing their thing, and that data gets into S3. Now, several times a day, we'll have these scalding jobs. Scalding is a Twitter library that lets you write Scala code that compiles down to MapReduce. These will run on EMR, and they'll get the most recent 8 hours of data, do some processing, write the results back to S3, where we then have this other process that will load that data into Redshift databases where it's made available to the world. We said we want to touch as little as possible, so we're just going to replace scalding with Flink. We now have this always-on cluster that just monitors S3, and as new files arrive, we'll grab them, do some aggregation, and occasionally we'll write results back to S3 where it's loaded into that same Redshift database. So from the outside world, it doesn't appear that anything has changed, just the data is getting from our bidders into Redshift more frequently. Of course, we might change some of this in the future, but for V1, this is really what we needed. Well, the first big decision you need to make when you go from batch to streaming is how am I going to window my data? How am I going to discretize it to perform aggregations? And we saw 2 ways of going about this. The first was an append semantic, where you say, I'm going to do something kind of like micro-batching, where I'll say every 5 minutes of data that I get, I'm going to perform an aggregation, output that results, and then the next 5 minutes move on. Now, this is really easy to reason about, right? I'm just adding these rows up. There's not a lot of state you have to handle. I only need to remember back in time 5 minutes. Now, in your database, you'll have multiple rows for each key. All of your queries are grouped by sums. Redshift can do that very performantly, so that's not a problem. The issue is, let's say I have 2 rows in my database that have the same key, and they both show counts of 10. There's no way of knowing if that is 2 different 5-minute intervals that just happen to both see 10 records, or if I accidentally inserted that row twice. That means we can't have the accuracy guarantees we need, and this was really a non-starter. Instead, we went for what we're calling an upsert semantic. So we window in 1 hour intervals, but we'll accept data up to 7 days late. So we have these very long-lived windows, and we're going to fire maybe hundreds of times over their lifetime, where we're constantly sending updates. All right, the count is 10, now it's 15, now it's up to 20. And in the database, we're constantly doing updates and replaces. This better aligns with streaming because now Flink internally in state always knows what the true value is. And as it changes in what we consider some significant manner, which means we've gone up by a certain percentage, or it's been so long in processing time since I sent an output, we can issue an update to the database. This works really well. We get the accuracy we need, but at least a much larger state, right? Now I have to remember what's happened the past 7 days at any given time. And so I need the right state backend. Of course, with Flink, that's RocksDB. We plugged that in, and it just kind of worked, right? We scaled up, got very large states. We did run into one interesting problem, though, and we're calling this the restore penalty. So Flink's running, everything's great. We crash for whatever reason. That's okay. We've been storing our checkpoints to S3. So Flink says, let me restore from the last checkpoint. It goes into RocksDB. Internally, RocksDB has 2 places data can sit, memtables, which are in-memory read-write caches, and then SST files, which is where the data actually sits on disk. Occasionally, this is fsynced, where the data from memtables is compressed and written. And so when we do a restore, that data goes into the memtable, and once it's there, RocksDB will tell Flink that it is restored and ready to keep going. It does not mean that an fsync is run. And so typically we're running these 4 core nodes, 1 task manager per core, and each task manager is an independent worker, so to speak. So there's multiple RocksDB databases per node. We'd restore, everything's great. We start running, we hit that first checkpoint after a restore. All these RocksDB databases have a lot of data in those memtables that has to be fsynced before a checkpoint can occur. And so 4 RocksDB databases, all fsyncing at the same time, we'd suddenly run out of memory, CPU would go to 400, yarn would kill the job. So we need a better RAM to CPU ratio, so to speak. And we said, you know what, for every 4 cores, we're only going to run 3 task managers. And we were worried that, oh no, we have to scale our cluster up, something terrible is going to happen. But what's interesting is we're in the cloud, right? We're a cluster in containers on virtual machines on Amazon. We lost a quarter of our virtual CPUs and had no noticeable degradation in throughput. But we now had that RAM to CPU ratio we needed, and we were able to successfully restore after a checkpoint, or checkpoint after restore. The one thing I forgot to mention, nothing is ever this simple when you're working on AWS. So you do this fsync. It may actually be going to another node, right? Your SSD might be the RAM on another computer. So there's all these network hops that Flink and RocksDB are not necessarily aware of. So we're in Amazon. That means we're interacting a lot with S3. It's where we read our data. It's where we write our data. It's where we put our checkpoints. It's important to note that S3 is not a file system. It likes to pretend to be a file system. It has a nice interface where you can do things like ls and rm, but it's not. It's really a key value store where you get a very high level of durability, but at the cost of eventual consistency. And Amazon makes some very specific promises about what it can and cannot do. Specifically, you're going to get read after write consistency for puts of new objects, but only eventual consistency for everything else. What this means in practice is if I write a new file to S3 and then I try to read that file, it's going to work exactly like you hope it does. But if I do anything else, it's going to take time for that change to propagate through the system. If you've ever worked with EMR, you actually get a consistent view. And so what happens is there's this DynamoDB table that's brought up, and all the changes you make to S3 are tracked in that table. If the table and S3 ever disagree about what the state should be, then we say, all right, S3 must be inconsistent. We'll back off and wait for things to resolve themselves. We needed something like this. And you know what? Flink is a stateful process. We expect it to always be in a consistent state. So why don't we roll our own file system, right? This is really a fork of Hadoop AWS, but we'll call it Flink AWS. And we're going to treat Flink like a source of truth. If it's trying to read a file and S3 says this file doesn't exist, then we're going to assume, you know what, S3 is in an inconsistent state. We'll back off and try again later. And this was like going from driving on a gravel road to driving on an asphalt road that has some potholes. It was definitely better. It solved a lot of our problems, but there were a couple big issues we couldn't work around. Specifically, S3 will not put an upper bound on how long it takes a file to become consistent. And this back off and wait is a blocking operation. We can't do it forever. we're eventually going to have to throw an exception and crash the system. The one big pothole in Flink when it comes to S3 is the bucketing sink, specifically the way that it manages state. So the bucketing sink is Flink's method for providing exactly one's output to a file system. And it does that by moving files through several stages. There are in-progress files I'm currently being written to. It closes and gets renamed to pending. Then after a checkpoint occurs, that file is accounted for. It gets renamed once again from pending to final path. That first rename from in-progress to pending is great. That's the first read after write. It's always going to be consistent. But that second rename, where it gets renamed from pending to final path, will never be guaranteed consistent. You just don't know how long this is going to take. And so we'd be running, we have hundreds of writers all writing out to S3. It would only take 2 or 3 checkpoints before we'd hit a single one that would take so long to become consistent that we'd end up throwing a checkpoint, throwing an exception. Of course, Flink can recover from that kind of error, but we don't want to be crashing and restarting the system every 20 minutes. So instead, we said, you know what? We're going to roll our own sink, and we're going to treat S3 like a key value store. We're only going to perform operations that we know it can, that will keep S3 in a consistent state. And you can think of this like a write-ahead sink. Things go, we're going to write them locally onto the file system of our node. Now, when a checkpoint occurs, we're going to close all those files, no matter how big they are. Some could be very big, some quite small. Copy all those files to S3. It's like a checkpointing sink, checkpointing sink, right? I'm bucketing by checkpoint. Now, we're not as fine-grained as the bucketing sink. It's an all-or-nothing operation. Either every sink successfully uploads or none of them do. And if we successfully upload, we'll write an empty done file in there just to signify that this is okay. If you only read the buckets that have the done files, you're going to get your exactly one semantics you're getting from the bucketing sink. And if you read everything, you'll get at least one. So you can kind of choose your poison there. So that got us most of the way, right? We're able to interact with S3. We have our very large state. We were ready to really scale up and start, processing our full data set. And then we stopped checkpointing, right? If you can't checkpoint Flink, game's over. We can't recover from failure. Our sink is now predicated on the ability to checkpoint. We can only get data that often. And this was the point in the process that we really got to dig into the internals, understand how Flink works under the hood. There's some tooling now where you can watch how checkpoint barriers flow through the system. That didn't exist at this point, so we had to build some tools ourselves. Cliff is going to talk about the details of what those tools are. I'm just going to talk about the results. And what we found is there were a small number of windows that were never checkpointing. So we took a step back, right? We thought we knew what our data set looked like, but that was really in the context of a batch process. I know how this data averages over 8 hours. What I don't know is how it looks in the span of 15 minutes. And what we found is we had very massive data skew, much larger than we expected. Specifically, 1/3 of all of our elements belong to 1/3 of 1% of our key space. But that 1/3 of 1% is constantly changing, so it's not like I can treat these couple keys special. In practice, what's happening is, right, 99% of our workers are getting 2/3 of our data, but 1/3 of all that data, those 1 billion records, are going to less than 1% of our workers, and they're just so overworked they never get a chance to checkpoint, right? The barriers just don't get there. So we came up with a 2-stage solution to solve this. The first was constraining our key space. We learned early on that Flink seems to really scale based on the number of windows, and luckily for us, we have 3 keys that are common across all of our reports. And we said that's going to be our primary key. Flink, regardless of what report we're running, is always going to key by that primary key. Internally, we can handle our secondary key and get the exact semantics we need, but Flink doesn't know about any of that. And so while this doesn't necessarily solve the problem, it at least makes it consistent across reports, so we only have to solve the problem once. Really, what we needed was to reduce the number of elements floating across the network. And if we were in Hadoop world, right, running MapReduce, we'd use a combiner, right? Do some map side aggregation, reduce the number of elements, then we do our shuffle and our final reduce. Flink doesn't have anything like that, but it does have the single input operator interface. This is that low-level interface that all the nice high-level abstractions are built off top of, right? Map, flat map, window are all just different flavors of this. And so by using this, we were able to build our own combiner implementation where we say, we're going to window by slot. Whatever elements just so happen to show up into the slot, I'm going to do some aggregations on them for just a couple seconds of processing time. And then we'll do our actual key and go into our real windows. As long as you make sure that what goes through that combiner is always an incremental aggregation, you can always use processing time. I need to keep the data moving because we're not using a keyed state backend here. We're using operator state. We don't get our asynchronous snapshots, so we need to make sure that we're not sitting in this combiner for too long. But if you go into a window, our window is still event time, and so we're getting the same semantics, even if on multiple runs, data flows through the different nodes. And by doing this, we were able to reduce the number of elements by between 80 and 90% flowing across our network, eliminated our skew, and got us running into production. So now Cliff is going to talk about some of the tooling that we had to build to run successfully in AWS.
Thanks. So when we wanted to run Flink in AWS, well, there's a number of considerations. First, in Flink, we're going to use standalone or yarn cluster. And then for storage, are we going to set up HDFS and make sure that's always up? Or are we going to use something like EFS, which is basically Flink's NFS, or S3? Then finally, how much do we want to spend? Are we going to have reserved clusters, or are we going to do just on demand so we can expand as we want? So use Spot. Most people would consider EMR here because you just spin up a cluster. There's only one problem with that, is that EMR costs you 25 cents on the dollar, or 25% surcharge of the on-demand price for the life of your usage of the instances, which in Flink's case is forever. So it just seemed to me a bit much to actually spend that just for them to have to install yarn for us. So for those who are not familiar with spots, I'll use an analogy. So imagine you are going to be you have a lot of kids and you want to take them bike riding. And so maybe you're a little cheap and maybe a little weird. You go to the bicycle emporium and you say, hey, you got a lot of bicycles here. I know you rent them for $10 an hour. I'll tell you what, I'll give you $1 an hour. And if you want them back, we'll be riding around here. Just come take them from us. So your kids all get a bunch of run to the little red bikes and start riding them. And then after a while, the guy comes out and says, listen, someone just offered $2. So he pulls all your kids off. They start crying. And that's why you don't use spots in production. Well, here's the thing. If your kids know how to ride the little red bikes, maybe they could ride the blue bikes, the bigger green bikes, tandem bikes. So when it increases the amount of inventory you can bid on. So if you look at, getting back to whether we're going to run Flink standalone or Flink on Yarn, that kind of made it obvious, because if you run Flink standalone, you're going to have to choose either 4 CPU instances or 8 CPU or 16 or 32 and sort of standardize on it, unless you wanted to have different outcomes every time you ran a cluster. So with Yarn, of course, you can just have, since every task manager is running in its own separate Yarn slot, you can work with 8 or any type of instance, and you'll have the same outcome. So how do you do this? How do you create a Yarn cluster just with a bunch of Spot instances? You don't want to pay EMR. You just so how is it done? Well, first of all, there's like a little concept of a cluster that I kind of made up so I could just do this. So to me, a cluster is so what is a cluster? You think of it as just a bunch of machines, right? Running some common software. Well, that's partly right. So a cluster is defined as one or more instances of a certain type of config, and it's keyed by name so you could just manage it, that group of machines. So this config is, in EC2, is called user data. It's something that you just submit as part of your request, and that's a shell script that gets called and run as root, on the instance when it's initialized. So that's fine, but the thing is, that's getting back to what a cluster is. A Yarn cluster is actually 2 clusters from this definition. There's the master, and this is a minimal Yarn cluster. The master, which is the resource manager, and then all the worker nodes, the node managers. So there's an extra concept here, which I call cluster join, and it's sort of like workflow join, which means that there's a block until one arrow in a workflow is finished, and then the other one can join to it, and then they can proceed. So it's basically that had to be implemented in order to create a cluster. So it's a simple implementation. So we have this little monitor. It's actually written in Go, and it runs on a micro instance, and it's called Spotty. Very creative name. And so if you see in this sequence diagram, what happens is that you'll request your cluster or both clusters simultaneously, your master and a bunch of worker nodes. They all have their user data, and they're all initializing. The thing about it that's slightly different is that the master, when it finishes, it'll just register itself and wait. Meanwhile, all the worker nodes, they're going to ask Spotty for join on the master. So they're going to block until the master finally registers, and then they're going to get the information they need, which in this case is just the host name, and proceed to their initialization, and then the cluster's up. Okay, so now you have your cluster, and you want to run Flink. So how do you do this? Well, you do this. The Spotty process will just do the same thing you'll do on your command line, which is initialize a shell process, and it'll, in this case, run it as in detached mode, and then manage it, or meaning kill it if it wants, via the Yarn REST APIs. Then everything after that is basically done through Flink REST. And it's pretty powerful. You can upload jars, and you can run your job all via REST, and then poll for everything you want to poll for using the monitoring API. Well, in our case, what we care about for recording in a database are exceptions and checkpoint events. Okay, so meanwhile, you'll also need to have some health checks. So you'll use the Yarn REST API to verify the cluster health, and then for us, there's Flink metrics gives you a ton of metrics, and in the UI it's great. You can see anything you want to know about what's going on in any of your operators. But for that bit about like being woken up at 3 in the morning, I just want to know that what's the current low watermark, because I want to know that we're proceeding apace and are processing all of our data. And I also want to know that check times aren't lagging, so in case we are proceeding, but checkpoints aren't, we're not going to be in for a big surprise should it fail. So there was something I had to do with the checkpointing. I'm sorry, with the watermark on it. It's a little trick to expose JMX as REST. Right now, you can actually go to the task manager. This wasn't available, but you could go to the task manager and do a query directly against it. But this made it easier for me because I could just do a wildcard via this little hack. It's basically a Java agent that you run as part of the Java init in Yarn. Just put it into the Flink conf. All right, so what happens? Well, I mentioned Spotty the monitor. Well, there's actually an agent that's also running on every instance. It gets pulled. It's just a single binary. It's Go. So it does the basic necessity if you're using spots of waiting for a spot reclaim. So it just does a regular poll, and so in AWS you can find out that you're about to be reclaimed, but only from the instance that's running. So it'll poll until it finds a 2-minute warning and then notify back so we can take action. It also supports what I call a POSIX pass-through, which is basically just a TCP for monitoring or REST for RCP of just calls you want to do on that node. Remember, it's run as root. We're running a VPC, so we can kind of do a lot of stuff this way. All right, so what happens when the cluster does fail over? Well, we get that warning, that 2-minute warning, and the first one wins. So here's the thing. Typically in a cluster, people would think, well, hey, we have to keep this cluster running. So if it were a Kafka cluster, I would do something like, register for another EBS, and then make sure that one finishes to coordinate basically the graceful turnover of a in a tumbling way. But for Flink, the nice thing with checkpoints is you can just start a whole new cluster, and that serves 2 points. One, you don't have to worry about cluster thrash when one node's dying and the other one's coming back. The other thing is it saves you a lot of money, because if you're getting reclaimed, well, chances are a lot of your others are going to be around the same timeline that you requisition that one. So you really want to start over again, and this makes it really easy. And it's actually the point that we're going to be starting over voluntarily pretty much fairly often. So anyway, so what happens, the general failover is that we'll initial cancel a save point, at the same time running bring up another cluster, so while one's save pointing, where the other cluster is coming up, when new cluster's up, we verify that save point's there, and then we restart the session, restart the job, and delete the old cluster's these 2 instances. and they may already be gone. This is a little slide. You've probably seen this before. This is just, generally, if you're running in AWS, you're working with about a 6.65 gigabyte footprint per task manager. You can decide how many slots you want, and that's where you gain your elbow room should you need it for your type of application. So the other thing about S3, the default implementation of S3 is what I call S3, serial, safe, and slow. It's the problem with running it is that you don't. The default implementation will write to a file, and when that's done, write to S3. So imagine all your RocksDB databases are being serialized to a file, which is not really a file. You see that cloud there represents. You're actually going over the network, and you're consuming IOPS, which is basically a resource that if you burst out of them, you're going to really hang in AWS. So what you want to do instead is and this is in general the case running Flink in AWS, do as much as you can in memory. Spread stuff around so you can use memory rather than disk. So in this case, you use what S3A is a library for S3 that supports something called, they call it fast upload. You could write your own of this, but basically it's in-memory multi-part upload. With S3, you can upload in multiple parts concurrently, sort of, just a commutative upload of multiple parts, and you could do it all directly from RocksDB serialized through memory to S3. So the only catch here is you have to be concerned, because if you get back to the slide with the heap, and you got to make sure you have enough memory for RocksDB plus your heap plus this little bit of pooled memory you're going to be using for your S3 upload. And then finally, Hadoop 3.0 has some really good code for S3. It's not out yet, of course, but and it's not easily backported, but it looks really promising. Okay, so finally, Seth mentioned some dev tools. Well, so what way this worked is it was a two-man job and two-person job, and what Seth would innovate some stuff in Flink, and then I would go and put it in the real world and see how it worked. And sometimes it needed some work that's how we found out about problems with serialization and checkpoints. It just slowed down. But the thing is, we didn't have much visibility into the processing in Flink because we didn't have the monitoring tools weren't really out in the UI yet. So I needed to write some tools so we could see some of the stuff. So how did we to do that? Well, we had live metrics, so we could see at least for all the task managers, which ones are running out of memory, which ones are pushing load. And then then there's also remote debugging. Each task manager is exposed a remote debug port, but that's tedious, and who wants to do that? So instead, for the most part, we use something. We developed a way of doing cluster logging. So imagine like Splunk or Sumo Logic, but really cheap, because this is spots and without any configuration, really easily done. So I call it Snoop Loggy Log, because it's not really a log, it's more like loggy. It's actually under the covers. What it is it's a logback appender that you just put in your Flink lib, and so you just use your regular logging, but you just register certain appenders in your logback.xml, and you'll see it coming back out. Under the cover, it's just running 0MQ, which is basically pure Java 0MQ, which makes it really easy to create sub-hub crazy network stuff. So what we'll do really quickly is I'll show that to you, if I can see how I can get my mouse working. Okay, great. Okay, so this is using a little WebSocket into that API, and I'm going to just Control+N. So I created a little cluster here, and this is basically a 100 core cluster. We go by cores. You see that it costs $1.19 an hour, and that's basically it. Otherwise, it's just a regular Yarn cluster that you've seen probably more times than you care to have seen. So now we'll start a Flink session. So the Flink session, I have this task manager override, which basically says out of the 4 cores per task manager, because we settled on here a min core size of 4, make it 3 slots. So as this is running, we can actually monitor this. here we go. So these little metrics here, this is what we use to actually see where we are in terms of like, right now it's like it's an empty task manager, it's 565 megs, it's the biggest memory footprint. So we'll run a Flink job, and right now this job is just, this is running in one of our dev clusters, and it's starting right now. So here's the Flink session, and this is all just pulled via the REST API, and then using server-side events just pushed to the UI. Sort of the same way, similar to how the Flink does it, but with a lot less style, actually a zero style. Here's the Flink job. You've seen it many times, and quickly, see that there's what we have a source, the S3 file watcher, which is going through a continuous file read, and timestamp watermark goes through a combiner, and then we go into our windowing, and then finally out to our sync. So this is running now. We start seeing some metrics coming through. So I'll go back to this UI, and this is where the logging was useful for us. So if I just enable this Snoop log, you'll see here all these debug outs. Typically, we run this from a command line, but these debug outs are actually showing Seth's combiner, and you're seeing these percentages. That's showing the actual reduction in network traffic. So the nice thing is here, the reason why we're just seeing that is because I just said com Flink MediaMath reporting equal debug. I could say debug on what we did for the checkpoints is we set that to the checkpoint coordinator, and we saw all the debug stuff from that we couldn't see. So we could see all the acknowledgments. And that's pretty much it.
Thank you.
Thank you. If you have any questions about just user data or anything like that, about how to run it, set up a Yarn cluster for cheap,
and all the Snoop logging is open source on our GitHub, so please use it. It's just as simple as updating your log back.
Yeah, this is it. All right.
Yeah.
So you've done a lot of work to kind of make the whole marketing sync work with eventual consistent file system.
Yeah.
Is there any chance you would contribute something like eventually consistency aware marketing sync?
Yeah. No. Right now we have, I think, more pieces of Flink. Yeah. Oh, sorry. So the question was, would we be interested in contributing some of like the eventually consistent bucket back? Right now, I think we have more of our Flink dist forks than I would care to maintain on my own. So I am more than happy to give it back to have community support, to keep these things maintained and up to date. Yeah.
In your Yarn session, do you run one job per session? Or you
Yeah, always one job per session. Yeah, because we sort of size the cluster for the job.
Yes.
What's your mean time to recovery when you have to do one of the when you have to do a spot check?
Well, so it takes about minute, 2 minutes for a cluster to come up, depending on availability and AWS.
And the size of your cluster.
And whatnot. Because our sync is predicated on checkpointing, it's really good motivation to make sure our checkpoints are fast. We typically sit around 30 seconds-ish, and then it's however long it takes Flink to restore when you start from a save point. So the cluster will come up concurrently as we're taking our final save point on the other. We're down for 5-6 minutes, maybe. Yeah, it's dominated by Amazon.
Yeah, I mean, this is, I think we're feeding. For reporting purposes, we can afford a little downtime. I mean, and it would be different, I think, if we couldn't. Yeah, we have a 15-minute SLA, so it's not, a minute here or there is not the end of the world. We're much more interested in making sure that our numbers are correct than fast, but fast is obviously great and cheap. Very cheap. Very cheap, yeah.
Yes.
How do you find the latest checkpoint since it might not have been from the campus?
So we,
Yeah, well, what happens is,
oh, sorry. So how do we find the latest checkpoint? We restart, save point might not have finished, we resume. There are only two pieces in the system that have to be highly available. That is S3, so not our problem, and a Postgres database that manages some metadata. So every time a checkpoint is taken, we have a table that has job IDs and has checkpoints. And we can always just, as long as that Postgres database is available, we can go and find the latest checkpoint. Yes?
You mentioned Postgres database to maintain the metadata. So what type of JDBC driver did you go with the JDBC driver or the JDBC? How did you do it?
no, that's actually in Go. There's a monitor that's polling the REST API to find out. Oh, sorry. What sort of driver did we use for Postgres? It wasn't in Java. It wasn't part of Flink. It's really just it's like a scratch. We just chose Postgres because RDS is really easy and simple. We have 3 tables: jobs, events, and errors. So it's just a poll to the monitor and just a place to put the information we find. The nice thing about the checkpoint poll is that it gives you could catch up in case for some reason you missed something on a, like you brought down the monitor and brought it back up again or something. No, this is entirely external to the process. So Flink's running completely unaware of any of that stuff. This is just a process that's running outside of that to poll and find information about Flink, so it can monitor the job. So what happens is that if it does find something wrong and it can't recover, it sends a message to something we call PagerDuty, and we get this message on our phones that says your cluster is down.
Yeah.
So I think it's running out of time.
Yeah.
Sorry, guys. Thank you very much. Could you give a thanks to
Yeah.
the please?
Thank you.